Good afternoon. My name is Stephen Omondi, and I'm a lecturer in Electrical Engineering Department. I'm going to present a subject known as, or a unit known as Electromagnetic Field Theory. And in Electromagnetic Field Theory, we have around 6 units supposed to be covered, and these units are vector field theory or vector analysis, we have electrodynamics, and this is the main core of electromagnetic field theory, because electromagnetic field theory involves 2 major fields, and these fields are electrostatics and magnetostatics. We are also going to look at another unit. Once we've looked at electrostatics and magnetostatics, we'll also look at Maxwell's laws or Maxwell's equations. Maxwell's equations. Apart from Maxwell's equation, we are also going to look at properties of waves. Properties of waves. And finally, our last topic in electromagnetic field theory is energy and momentum. Energy and momentum in electromagnetic waves. Now, without wasting a lot of time, now we can go exactly to the first unit that we are supposed to cover, which is vector analysis. Vector analysis is very important in electromagnetic field theory because all the rest of the units will involve forces. So as we know that vector already is a force in its own. So we are going to look at some few terms related to vector field analysis, and these terms are very simple. We know what is a scalar. A scalar, so we can define a scalar as a quantity that only has magnitude. Is a quantity with only magnitude. That is a scalar quantity. Then we are also supposed to look at other definitions like what? Vector itself. So a vector is a quantity with magnitude and direction. And direction. That is a vector. And also, we also need to define what a field is. So we can say also that a field is a physical quantity just like we have a scalar is also a physical quantity. So when we have a scalar, a field that is purely, let's say, that is purely made of like a scalar. Here, a scalar, we can also give an example of a scalar can be like temperature. We also know that a vector, we can also have example of a vector being what? A force. So if we have a purely scalar field or a temperature field, we can say that is a physical quantity that can be known as what? A scalar field. We can equally talk of, if it's a physical quantity like force, then we can talk of that as being a what? A vector field. But in our discussion of electromagnetic field theory, in our discussion of electromagnetic field theory, we are basically going to look at two types of fields. Now, we have these two types of field are the electric field, and we also have what? A magnetic field. So, because they are all vector field, we'll normally denote that electric field is denoted by capital E with a bar or an arrow on top. This arrow indicates that it's a vector field. Similarly, a magnetic field can be denoted by capital H with a bar on top. So this indicates that this field is equally a what? A vector field. Now, because electromagnetic field will only involve vector fields mostly, then it is necessary to know a lot of vector analysis before handling some of this. Handling the other units that we'll look at later on in electromagnetic field theory. Now, some of very important things that we need to know in vector field, one of them is unit vector. So what is a unit vector? So when you're talking of a unit vector, it is a vector, a unit vector is a vector whose magnitude is unity. It is a vector whose magnitude is unity, and its direction is along the vector. Now, assumption here again is that anybody doing electroengineering at a diploma level, you are also covering vector field analysis partly in mathematics. So when we are looking at this now, I'll assume, now let me say under unit vector, just say assume Cartesian coordinates, then I can say that let A bar, that is a vector, be represented as A of x in the direction of AX bar plus A of y in that direction plus A of z in the same direction. Then our unit vector, I'll represent that as A, with that A bar will be represented mathematically as 1 over the magnitude. Double lines in a vector stands for magnitude of that. 1 over that magnitude of A bar. So if we write this, we can write this as being equal to, let me say where A bar, that magnitude, is represented as the root of AX squared plus AY squared plus AZ squared, like so. So then, to represent that, now if we are to write our unit vector, we are going to have our unit vector being the same as A, it is A of A bar will be AX. Now this is the direction we are saying. We've said that along the direction of the vector. So this is the direction of the vector. Now I'm writing first. Then we have AY of that. Then there is AZ of that all over the magnitude. So that is how we are going to represent our vectors. So we are saying that this is AX squared plus AY squared plus AZ squared, like so. So that is our unit vector that we've represented there. Then very important again that we need to know under vector analysis is addition and what? Subtraction of vectors. Addition and subtraction of vectors. So maybe we can say, let A bar be represented as that. We still have that AX bar plus AY that plus AZ that, and B bar be represented as BX AX plus BY AY plus BZ AZ, like so. Then now if we add the two, now we can say addition and subtraction, we can just use this. We can say now if we are supposed to add vectors A plus B plus or minus vector B, then it's just like the way we do algebras, yeah? Now we'll be doing this. We'll say that it's AX plus or minus BX of that plus into AY plus or minus BY of that plus AZ plus or minus BZ of that. So that is how we'll be adding vectors. Yeah? And similarly, again, apart from that, apart from addition of vectors, as we've done it there, we'll also look at multiplication of vectors. So if we multiply vectors, so how are we going to multiply our vectors? Vectors can be multiplied in two major ways. So we have that a vector can be, we can talk of a vector being multiplied as a scalar, multiplication by scalar. Remember we said a scalar has no direction. So multiplication by scalar. Two, we have multiplication by what? Vector. So the first one, multiplication by scalar. Say that multiplication by scalar, then you can say if A bar is a vector, and K is a scalar quantity, then we can say that K, sorry, before that, maybe say where, yeah, we can say where K, sorry, where A, I'm sorry for that, A bar is equals to the same term we've used as our AX plus AY of that plus AZ of that direction, then where that is that, then K A bar must be a multiple of this, just that the direction will be the same. So it's only, we've just increased the magnitude by the value of k. Yeah? So that is how we can multiply that as multiplication by scalar. Then if we are supposed to multiply, now multiplication by vector, you can have it here, multiplication by vector. So multiplication by vector. So if we are to multiply by vector, then we also have two different ways. If you're supposed to multiply by vector, there are two ways of doing so. We have one, dot product. Then the second one is cross product. So these are the two ways that we can multiply a vector through dot and cross product. So very simple. The first one, our dot product. Now from our own basic mathematics, we can say if we have two vectors, say A bar dot B bar is the same as the magnitude of A multiplied to the magnitude. Remember we did magnitude there when we started, magnitude of B, the cosine of theta. So this is how we do our dot product mathematically, and then we can say where theta is the angle between the vectors, where theta is the angle between the vectors. So that is how simply we can multiply two vectors using dot product method. Again now, apart from dot product, we say that again we can also have what? Cross product. And cross product, we normally also call it as the curl. Now in cross product again, what we are saying that a vector A bar cross vector B bar. This, if we assume Cartesian coordinate system, then we can say that this can be rewritten as AX bar, the direction, AY bar, AZ bar. Then we have the magnitudes of that particular one, AX, AY, AZ, BX, BY, and B what? Z. If we enlarge that properly, if this is supposed to be enlarged again so that we can see what is happening there under cross product, because it is a bit like mathematical using the determinant method. So this can be rewritten as, which is equals to the determinant of AY, BY, AZ, BZ of AX bar minus AX, BX, AZ, BZ, that in the direction of AY, then we have plus, we have AX, BX, AY, BY in the direction of AZ. And if we are looking this, if you are so keen now, if you are to get the real determinant of a 2 by 2 matrix, because it's almost like a matrix method, this is the same as having what? We normally start with AY, BZ minus AZ, BY in the direction of AX, again minus AX, BZ minus AZ, bx in the direction of ay, then plus ax by minus ay bx in the direction of what? Az. So this is how we normally handle our multiplication of vectors using dot and cross product methods. Dot and cross product method of vector analysis. Now, there are rules that are necessary to be followed when we are doing dot and cross products. So maybe we can look at those rules. So we can say that rules to be followed, on dot and cross product. Rules to be followed on dot and cross product. Now, say if ax bar, ay bar, and az bar are unit vectors, along x, y, and z directions, that is Cartesian coordinate system. We look at other coordinate system. So you're saying that they are along x, y, and z directions. Then, if we start with the dot product, the dot rules, then ax dot ax, there's a bar on top, must be the same as ay dot ay, which is the same as az dot az, and this is the same as 1. So if we dot similar unit vectors, then we'll get 1. So say, again saying that similarly, ax dot ay is equals to ay dot az, which is the same as az dot ax, and that should give us what? 0. So those are the rules. These are the two rules that we use in dot product method. So we also want to look at rules for cross product. Yeah? So in our rules for cross product method, so again we can say that in cross product, if I have ax cross ay, that gives me az. Similarly, ay cross az should give me ax, and az cross az cross ax will give me ay. If we do the opposite, then we'll have ay here cross ax will have negative az, and az cross ay must give us negative ax. Similarly, ax cross az will give us negative ay. You don't need to cram this. It's very simple. What we are having here, as a student, you should just know how to draw a cyclic permutation. So we have ax. From ax, we can go straight to ay. From ay, then we have az, and you can do a cyclic permutation like so. So that we are saying that ax cross ay, the one crossing, which is the opposite, is the same as AZ. Similarly, AY cross AZ will have AX, and AZ cross AX gives us what? AY. Now, if we change the direction now, in the opposite direction, we get the negative values. That again will have the negative value, which is now AX cross AZ, will give us negative AY. If we go AZ cross AY, then we'll get negative AX. Put a bar on top, show that it's a unit vector. We normally call this as the cyclic permutation method. Cyclic permutation method. So these are the rules of to be followed when applying dot and what? Cross product. These are the rules that one should follow when applying dot and cross product method.